Welcome back to Codex. Next up, we have another talk that was rescheduled from the 2022 JMM special session on recent advances in packing. Our speaker is Emily King, who is an assistant professor in the math department at Colorado State. Professor King studies harmonic analysis, data analysis, and signal processing. Within the Codex community, she's known as a driving force towards algebraic, geometric, and combinatorial methods in frame theory. Today, she will tell us about various combinatorial aspects of equiangular tight frames. Take it away, Emily.
All right, thank you for the introduction. I'm going to keep this talk in sort of in the spirit of JMM, so I'm not going to push it too long. So there'll be a little bit of time for questions and breathing room between my talk and the following talk. So there'll be some of these topics or a lot of them we're just going to be lightly grazing over. Okay, so if you've seen me give a talk on frames, you have most likely seen me talk about this set of 9 vectors in 3-dimensional space because there's just so much mathematical structure packed into these vectors. So I'm going to call this G3. And this set of vectors, all of the entries are 0 or 6th roots of unity. To be more precise, we have plus or minus some sort of pick your powers of some favorite primitive 3rd root of unity, say e to the 2 pi I3. And we're going to talk today a little bit about why this collection of vectors is so nice. But it is nice in harmonic analysis, and in particular for the purpose of this talk, has certain substructures that are nice combinatorially. Okay, so just kind of jumping right in, what is an equiangular tight frame for a span? So the for its span is the component of this definition that is maybe not as standard for this community. So we're going to take a collection of n vectors in d-dimensional space. And we say that it's a tight frame for its span if there's some non-negative alpha and some positive a, such that whenever we take the inner product of any 2 of those vectors, the absolute value of that inner product is either equal to 1 if it's just the vector in itself, or equal to alpha otherwise. And also we have that if we take any vector x that's in the span of these vectors, we have this really nice change of basis formula that looks a lot like what we get with an orthogonal basis. So we say that x is 1 over that other constant that we selected, a, times the sum of the inner products of x with the particular vectors vj times vj. So if the span of these vectors is the entire ambient space FD, then we just call the set of vectors ETFs. But here it'll also be really important for us to look at sets of vectors that span spaces that are smaller than their ambient dimension. So what are some examples of equiangular tight frames? So the most classical one that you learn as the very first moment you learn about tight frames is the so-called Mercedes-Benz frame, or as I like to represent it, rotated to the cubic roots of unity. So we have a vector pointing out to the left, and then every 120 degrees, we have another unit vector. And these are an ETF for all of R2. We also, if we take these antipodal points of particular platonic solids, and for each pair of antipodal points, we choose a vector, and we shoot a vector from the origin to that antipodal point, then that collection of vectors is going to be an equiangular tight frame for all of R3. And this set of 9 vectors in 3-dimensional complex space that I mentioned before as an example of an equiangular tight frame for all of complex space. Now let me back arrow for a moment. So one example of an equiangular tight frame for a span, which is not an equiangular tight frame for the entire space, is if we look at the first 3 vectors here of this set of 9 vectors in 3-dimensional space. So the set of all 9 vectors has as an absolute value inner product 1/2. So any subset is also going to have that property. But there are a number of different ways that you can see that these vectors actually have a very nice change of basis formula with respect to their span, which is the two-dimensional subspace of C2 with the second component being equal to 0. So here we have 9 vectors that are equiangular type frame for all of C3, and then we have 3 vectors that are equiangular type frame for their span, which is a two-dimensional subspace of C3. Just one more comment about coherence. We're going to need this later on when we talk about subspaces. So if we just consider the collection of sequences of n unit vectors in either d-dimensional real or complex space, then the coherence, which is sometimes called the maximum correlation of that collection of vectors, is just the largest in absolute value inner product between any two vectors that are distinct. This is equal to the maximum of the cosines of the non-obtuse angles between the line spanned by the vectors. So let me say a little bit more about this. So you might remember from calculus, if you take the inner product of 2 unit vectors, then what you get is the cosine of the angle between them. But we actually don't, we want to work with vectors because they're easy, but what we're really thinking about are lines. So if we look at this vector x in red and this vector y in blue, what we really care about is the angle between the lines spanned by them. So what we want is we want this orange angle theta, not this green angle phi. And if we take the inner product of x and y, what we get is the cosine of the green angle phi. But if we take the absolute value of that inner product, then what we get is the cosine of this angle, orange angle theta. And it is a fact that whenever we have an equiangular type frame, they minimize coherence. So amongst all sets of sequences of n vectors and d-dimensional space over the real complexes, they minimize that. Okay, so going back to this example, we have these 9 vectors in 3 dimensions. The first 3 vectors, as I mentioned already, form an equiangular type frame for their span. So we can ask the question, when are equiangular type frames for spans contained in ETFs? And this answer has implications for a number of fields. First, for compressed sensing, I express this in orange rather than the prettier blue, because when these subcollections exist, that means that a matrix has what's known as low RIP or low spark. And so these matrices are not good for compressed sensing in its traditional sense. But for more maybe fun or entertaining thing, whether or not these ETFs for spans are contained in ETFs have implications for optimal Grassmannian and spectrohedral packings, quantum information, and extremal combinatorics. So focusing on some of these blue words. So in other words, the Grassmannian spectrohedral packings were asking, can ETFs for spans that are contained in larger ETFs be used to create optimal subspace packings? And with quantum information and extremal combinatorics, the question is, can ETFs for spans that are contained in ETFs be used to prove the existence or non-existence of ETFs of certain parameters? Okay, so one of the constructions that we're going to see today, actually the only actual construction, involves so-called difference sets. So this is the first combinatorial object that we're seeing in this talk. So what is a difference set? So let's fix a finite abelian group G of size V and a subset D of size K. So subset, not subgroup. We're going to consider the multi-set of differences of elements. So since G is abelian, I'm writing differences because I'm writing the group operation to be additive. We consider the multi-set of differences. So by multi-set, I mean if a number appears, can be written a few different ways as a difference of distinct elements, then that would be counted multiple times. So we say that the set D is a VK lambda difference set if the multi-set of differences contains each element, non-identity element of our group lambda times. So let's look at a silly trivial example. If we look at the cyclic group on order 3, and if we just throw away the 0 element, then what we get is a 3, 2, 1 difference set. So the group has 3 elements, our subset has 2 elements. And if we look at all the possible differences, we see we get the difference 1 and the difference 2 each one time. The first sort of non-trivial difference set that we can consider appears in the cyclic group on 7 elements, and it has 3 elements. So 1 possible example of this is the set 0, 1, and 3. And if we look at all of the differences, so 0 minus 0 is 0, 1 minus 0 is 1, 3 minus 0 is 3, and so on and so forth. And if we look in this difference table, we see 1, 2, 3, 4, 5, 6, each all appear exactly once. So hence, this is a 7, 3, 1 difference set. But we don't have to just stick with cyclic groups. We can also look at non-cyclic groups. And so in particular, some non-cyclic groups that we like because they lead to nice looking frames are different powers of Z2. And if we look at Z2 to the 4th, and we write out sort of tuples just as strings of zeros and ones, then we have this set of 6 tuples that forms a 6, 16, 2 difference set, meaning the size of this group is 16. There are 6 elements in this set. And if we look at all the differences, we hit each non-identity element exactly twice. And if we take the complement of this, so anytime you take a complement of a different set, you get a different set. And the complement of this is a 16, 10, 2 different set in the same group. Okay, so to turn these different sets, these combinatorial objects into nice frames, we need something else, another ingredient. We need so-called character tables. So we're going to again fix a finite abelian group G, and we're going to let G hat be the group of homomorphisms from G into the unit circle in the complex plane. Then the character table of G is the square matrix with rows labeled by the elements of the group and columns labeled by the elements of the dual group. And the entries are just the pointwise evaluations. So the classical example is if we take our G to be a cyclic group, then what we get is, depending on how you like to scale Fourier transforms, you get the n by n discrete Fourier transform matrix. Another sort of class of classical examples would be if we take any of these groups that we're building up as powers over Z2, then we get the 2R, 2R, and I realize I'm mixing up the capitalization of R's here. Sylvester Hadamard, which is the R-fold Kronecker product of the matrix 1, 1, 1, minus 1. And you might notice that matrix because it's codified in blue and red circles on the Codex website. So if we take one of these character tables and we remove from it a set of rows where the rows are indexed by some set D, then this forms an equiangular type frame. The columns of it form an equiangular type frame if and only if that set of rows we took was a different set. So 2 examples are, if we look on the left, even if we take this very, very trivial different set that was just, hey, let's just throw out 0 from the cyclic group of order 3, and then we look at that character table and then we appropriately scale so we get unit vectors, then this forms an equiangular type frame that we call a simplex ETF because there's one more vector than the dimension to span. And we do the same thing with that first non-trivial different set of 3 elements in the cyclic group of order 7. And this set of 7 vectors in C3 is a different set. Now, this set here on the left in blue should actually maybe look a little familiar, because if you shove in some zeros and assign some things, then what you get are the different columns that we had in that set of 9 vectors in 3-dimensional space. Okay, so let's let phi be any equiangular type frame. Then any subset of k vectors which span a k-1 dimensional subspace are an ETF for the span. So we get that change of basis formula automatically when we play this game. And we call it a k-1 regular simplex ETF. So the sets of subsets of vectors, or the corresponding incidence matrix, which are k-1 regular simplices, is the binder. And binders sometimes themselves form very nice combinatorial structures like balanced and complete block designs, and also may be viewed as a slice of an equiangular type frame's matroid, which is another combinatorial object. So matroids, like one way that you can think about them is by encoding sets, minimal sets of linearly dependent vectors. And in a sense, these the binder is encoding what are the smallest minimal sets of linearly dependent vectors. So let's go to this, back to this set of 9 vectors in 3-dimensional space. So we can just see by inspection that these first three vectors must span a 2-dimensional space, i.e. the subspace of C3, where the second element is 0. And again, my inspection, we can see that the second set of 3 vectors has the same property, although the 2-dimensional space they span is the one that has 0 in the third component. And then finally, we can see the same thing for the last set of vectors. So what might be surprising is that actually there are 9 other subsets of 3 vectors that have that same property. So it's a little harder just to glance at it, see. But the one set that's still somewhat easy to see is we take the first vector from each of these sets. We could see we get a 1, 0, -1, -1, 1, 0, 0, -1, 1. And if we add those vectors up, we get the 0 vectors. So that tells us that they span a 2-dimensional subspace. And we can continue this. So what we're looking at here in this blue and yellow grid is just a way of codifying what all of these simplex ETFs are that are contained. So as we move across the 9 columns, I say yellow if this vector is in a set that is in that is spanning a 2-dimensional space, and blue if not. And then the rows are the 12 different sets of this form. Okay, so it ends up when we're lucky, we have something really special going where we have different sets that are forming an ETF, but also different sets that are telling us how to find special subcollections of vectors. So let's let D be a different set for some finite abelian group, and E a different set for its dual group. So those are all the homomorphisms into the unit circle, which is necessarily also a finite abelian group that is actually isomorphic to the original group. So let's form a set psi by first removing the rows indexed by the different set D, and then the columns indexed by the different set E, and then appropriately scaling them so that they all are unit vectors. So if these vectors of psi form an ETF for their span, then we call D and E paired different sets. So what we're looking at here, the pluses here stand for +1 and the minuses stand for -1. And if we look at the set of all the pluses and minuses, what this is taking out the rows that correspond to that 6, 16, 2 different set that we saw earlier, or we're told that existed earlier in Z2 cross Z2 cross Z2 cross Z2. And then the orange columns, they correspond to a different set for G. In fact, they correspond to this different set that was the 16, 10, 2, but in the isomorphic copy of that in the dual group. And whenever we get this, we actually don't just get one ETF for the span, but an entire family. And this family actually has certain nice geometric properties. So let's rework the geometry of vectors. Let's take a unit vector, an RD, and define the orthogonal projection onto the span of that unit vector. So all we need to do is we just take that vector times its adjoint. Okay, so what we're going to say is we have 2 different vectors, phi and phi k, and then we form the orthogonal projections onto their spans. And we are going to look at the square of the Frobenius norm of their difference. So the Frobenius norm is just you're multiplying these things together and you're taking the trace. And so if you work this out, then it becomes, this is the trace of pj squared minus 2 times the trace of pj times pk plus the trace of pk squared. And if you work everything out, then what pops out at the end is that this amount is equal to 2 times the square of the sine of that non-obtuse angle between the lines spanned by these vectors. And this ends up giving us a way of defining distances between the lines that are spanned by these vectors called the chordal distance. So the chordal distance is just, well, we have a square here, we get a 2 here, we want to get rid of it. So it's just the sine of that non-obtuse angle, which we can write as 1 over square root 2 of the Frobenius norm of the difference of these 2 different projections. So let's let GRD denote the Grassmannian of R-dimensional subspaces of RD. So before we were talking about lines, so they are 1-dimensional subspaces, or they're the projective group. Then for any subspace, WJ in the Grassmannian R-dimensional subspaces of RD, this actually could also hold over the complexes. So that should be an FD. Let PJ denote the orthogonal projection onto that subspace. We can just take the formula we had that worked for lines and apply it to these subspaces. So we define the chordal distance as 1 over square root 2 of the Frobenius norm of the difference of these projections. And it ends up, without too much work, you're playing around with properties of traces. One can prove that if you have a collection of endpoints in the Grassmannian, then there's an upper bound, there is a lower bound to how small that can get. And collections which saturate this bound are called equichordal tight fusion frames. So let's go back to this pair different set collections. We let D and E be pair different sets. So D is a different set in G, E is a different set in the dual, and they play this game together. Then let's form psi sub chi by removing the rows indexed by D and the columns indexed by chi E. So if E is written multiplicatively, then this is chi E. If it's written additively, it would be chi plus E. So we're just shifting around this different set by each possible element of the dual group. And then we appropriately scale the vectors so that they're unit vectors. Then this collection of subsets is a collection of equiangular tight frames for their spans, and their spans are subspaces which form equichordal tight fusion frame. In the example that we saw above, depending on whether or not we choose D or E as being in the group of the dual group, then we get 16 equichordal subspaces of dimensions 5 in R6 and 16 equichordal subspaces dimension 5 in R10. Okay, so here's just flashing through a bunch of different slides to make sure that I keep within the time. Just a little bit of teasers of things that I think combinatorics can be useful in frame theory. So first of all, matroids are ways of encoding linear dependencies of vectors, and matroid theory may be used to prove results about frames. So for example, one can really dig into linear algebra and prove precisely that the Naimark complement of a full spark frame is full spark, or it just falls out automatically from matroid theory. So once you know about matroids, then you're able to prove more things and not even get into the linear algebra. Also, honeycombs characterize the spectra of sums of Hermitian matrices, and they can be used to prove results about decomposing frames into frames with their spans. So if you loosen up this question about equiangularity, we can also loosen up what we're talking about. Instead of looking at packings in the Grassmannian, we can loosen that up to packings in the spectrahedron. And it ends up spans of embedded ETFs sometimes yield optimal spectrahedral packings when they don't necessarily yield optimal Grassmannian packings. And finally, various results in extremal combinatorics dealing with line configurations and may be proven by analyzing substructures like simplex ETFs. So this is something that a former postdoc and I have worked on, but this is not a unique idea. I mean, Lemons and Seidel first started by saying, we have these sets of equiangular lines, and we want to consider maximal subsets of these lines where all of their inner products are negative, which in some cases ends up being a simplex equiangular type frame. We also have this nice conjecture from Neil Gillespie that says that if we have a sort of maximal collection of equiangular lines in real Euclidean space, and then we impose an additional constriction that we want this set of lines to have a subset of lines where all of the inner products are up to equivalence positive, then we only get a finite number of things that satisfy that. So the conjecture is that perhaps by understanding these subcollections of vectors, we can disprove the existence of certain solutions in extremal combinatorics. All right, so I actually went a little bit longer than I wanted, and I thought I'd cut out a whole lot. I don't think I got into any details, so there's barely any information, yet somehow, like, here we are at the end of the talk. So anyways, thank you for your attention. There's my website there, and here is a listing of some of the papers that I either specifically mentioned or vaguely referenced.
Great, thanks for the talk. Smash this reaction button. Stop the recording.